I will disappoint Madhu slightly because I'm not going to talk about our algorithm in this presentation. And the reason is that I was given two options. One was either to give a technical talk about our algorithm, and then I get 30 minutes. Or give a very general talk without any formulas, and then I get an hour. So I preferred the hour because as an academician, in general as a researcher, I think all of us like to speak. So this talk is going to be completely non-technical. Although can it somehow move this side? Or does it stay this way? It will probably stay this way, okay. Oh, thanks. I have cheated a little bit and I have put a few formulas in this, but not many. So I'm going to give a history of primes, and while I started with this great aim of covering the history of primes, but pretty soon I realized that it is really impossible. So this title is not the representative of the talk. It's really a brief history of prime. So what are primes? We all know that a number is prime if it is greater than 1 and is divisible by 1 and itself, no other number. Otherwise, we call it a composite number. And 2, 3, 5, 7 are the examples of the first few primes. So why do we want to know about primes? Well, the reason is the fundamental theorem of arithmetic, which tells us that every number can be written as a product of prime numbers in a unique way. So prime numbers are a kind of atoms which compose together to make all the numbers. You can think of them as building blocks also. So it's fairly clear that to understand the general property of numbers, we need to understand prime numbers. So where are they? Well, amongst the first 100 numbers, this is the exhaustive list of primes. I am sure it's really difficult to go through them and make some sense out of. So here I have taken some simple observations from that list. That there are 25 primes less than 100, which is 25% exactly. Should move here. Of these 25 primes, 4 are less than 10, which is 40%. 15 are less than 50. 21 are less than 75. So if you just notice the percentages, the fraction of primes appears to be going down as we increase the interval size. And here are some questions about the primes. The first one, how many primes exist? More interesting one, can we estimate the number of primes less than number n? Third, well, given a number, how do we find out if it is prime or not? And fourth, how do we generate all primes less than a given number n? These are 4 very simple questions, and I will speak around these questions in this talk. One can of course come up with many other questions, but I am going to restrict myself to the history of these 4 questions. Now, primes have been of interest to mathematicians right from the beginning, and even the ancient Greeks have studied the prime numbers in great detail, and some of the earliest results about prime numbers come from them. So in Euclid's compilation of the mathematical results during Greek time, in his book Elements, there are two very basic results about prime numbers proved. One is the fundamental theorem of arithmetic, and he also proved that there exist infinitely many primes. And that clearly answers the first question. Then, around 230 BC, in the same school as of Plato, I think, Eratosthenes came up with a method which is referred as the sieve of Eratosthenes. This method allows us to compute or generate all prime numbers between 1 and n. And it's an extremely simple method. Write down all numbers from 2 to n, and we'll start crossing them out. So we take the first uncrossed number, say p, and cross all multiples of p except p. And then take the first uncrossed number again, cross out all its multiple, and keep doing it until we cannot cross any other number. Whatever is uncrossed are all primes. So let's look at the sieve at work. In fact, this is exactly how I generated those prime numbers less than 100, which I showed you a few slides earlier. So it's a really useful method. So here is all the numbers between 1 and 100 written down in a nice order. The first number here is 2, which is prime, and let's cross out all multiples of 2. Okay, they go out with a sound. Okay. So all the multiples of 2 are gone. We have these gaps there. Now the first uncrossed number, so I'm coloring the number red to represent that they are crossed out. Sorry, the crossed outs are vanishing, and 2 is we have already covered. So the next number is 3, and the multiples of 3 now go out. The next number is 5, and there go out the multiples of 5. Then 7. Then the first number is 11, and in fact there are no multiples of 11 here. The next number is 13, which has to be a prime number, and there are no multiples of 13 either. In fact, there are no more multiples here. All the numbers which are left on this screen are all primes. And this is a set of all primes, less than 100. It's a very simple and elegant method for identifying primes in a certain range. And this clearly answers our question 4 also, because the question 4 was, how do we generate all primes between 1 and n? And in fact, we can use this method to answer question 3 as well. Question 3, if you recall, was how do we know if a number n is prime or not? Well, here is a method which generates all primes between 1 and n. So what we do is simply write down all the numbers between 1 and n, run the sieve, identify all the numbers, all the prime numbers in this range. If n occurs there, then n is prime. If n doesn't occur there, it's not prime. But this is cheating a little bit, because we are only interested in knowing if n is prime. We don't want to know all the primes less than n. This method is giving everything to us. So perhaps there is a faster method, or some, intuitively faster method, which doesn't really generate all primes less than n, which will tell us if n is prime. So let's say question 3 is partially answered, but we'll still look at, and this idea or this question has been studied later on as well, so we'll continue looking at it. So question 2 is still not clear at all, that how many primes are there up to n. And question 3, which I'm going to now modify slightly in view of the sieve method, that how to quickly know if n is prime. By quickly, let's intuitively understand what it means. And as you see, these 2 questions out of 4 were already answered by the ancient Greeks, and one could argue that that was just the beginning of the mathematics. So one should expect, or one could expect, that the remaining questions will also should not take too much time to be answered. And that's a very right expectation, and that's how it would have happened. except for it's really dark there. So for the next 1800 years, almost nothing happened about prime numbers. Much is not that the development mathematics stopped. Lots of mathematical ideas came about, for example, the concept of zero and many other interesting things. But somehow mathematicians did not feel like studying prime numbers, or for whatever reasons. There were other reasons also, there were political reasons and other things, that people were more interested in doing things much different from mathematics. Okay, so nothing happened really up to 1600. And then suddenly, as if the gates opened of something which was being held up for a long time, there was great progress made on prime numbers. And the first contributor was Pierre de Fermat. He is famous for, of course, his last theorem. But there is a very simple result that he proved, but it's a very elegant result. It's referred as Fermat's little theorem. The theorem says that take any prime number n, take any other number a, and compute a to the n modulo n. Get back the number a. It's really an amazing result. No matter what a is, no matter which prime n we choose, compute the nth power of a, compute it take modulo n, which really means divide by n and take the remainder, and we get back the number a. I find it really magical, because once you see the proof, then one can say that, okay, it's not what's so great about it. But if you just think about it, it's really amazing. So for example, 2 to the 5 modulo 5 is 32 mod 5, which comes back to 2. 3 to the 5 mod 5 is 243, which again comes down to 3 when you divide it by 5 and take the remainder. 2 to the 11 mod 11 is 2. 4 to the 7 mod 7 is 4. Right, so apart from its seemingly magical properties, we can also hope to use it as a test for primality. Because this theorem says if n is prime, then it satisfies this property. So what about the following test? Given n, let's choose some a, compute the nth power of a modulo n, and check if it equals a. If it is, then if it is not equal to a, then we know for sure that n is not a prime. If it is equal to a, then perhaps we can conclude that n is prime. So let's just define our test in this way. In fact, interestingly, ancient Chinese about 400 BC or that period believed this to be a right test for primality, where in fact they believed it for a equals 2. That is, if 2 to the n equals 2 modulo n, then n is prime, otherwise not. But before looking at this, let's first see if it is really quick. Quick in the sense we said that the sieve of Eratosthenes can be used for testing primality of a number, but is not quick in the sense that it takes a long time, generates all the numbers between 1 and n. So is this test really quick? Because here we need to take the nth power of a, which if you think about it, you multiply a with itself n minus 1 times. Secondly, the other problem is that the number a to the n could be extremely large, even for small a and small n. But there is a simple workaround to these problems, which is we call it the repeated squaring trick in computer science. That start with a, compute a square, go modulo n, so it's a small number. Then multiply that number with itself, and that will give us a to the 4. Then multiply that number with itself, that will give us a to the 8. So we can very quickly compute a to the n. Okay, unfortunately, the test is wrong. And that's because of karmical numbers. Korsalt and Carmichael around 1900 noted that there are some composite numbers also which satisfy this test. And Carmichael was the first person to actually give such numbers. 561 is the smallest such number, and these numbers are named after him. And fairly recently it has been shown that there exist infinitely many Carmichael numbers. So we cannot really use this simple test as a test for primality. So what about a formula for primes? The prime numbers are, if you just look at their occurrence on the number line, they, on the face, on the looks, at the first glance, they appear very chaotically distributed. Sometimes they occur very close to each other, sometimes they occur very far to each other. There is no clear pattern amongst them. Now, the question I am posing, and which has been posed also, is that does there exist a nice formula for primes which captures them completely? So the formula should be such that if you plug in the number into that formula, it should tell you whether it's a prime or not. And if such a formula exists, then hopefully we'll get an answer to question 3 as well, because we can just plug in the number into a formula and see if it says, the formula says it is prime or not. Say the formula is 0 if it is not prime, say it's 1 if it is prime, something like that. Because of the very chaotic distribution of prime numbers, this quest for formula turned out to be very hard. What people tried to come up with the formulas, but either the formulas were not very nice or they couldn't get any formula at all. Pharma suggested, for example, the following formula. It is not for all primes, but only for a subset of primes. So he said that if you look at the sequence generated by 2 to the m plus 1, where m varies, then this sequence contains only prime numbers. Of course, at that time there were no calculators available. One could have simply verified that just for m equals 5, this is not a prime, which actually Euler noted nearly 100 years down the line. In a similar vein, a contemporary of Pharma, Mercenary, studied primes of the kind 2 to the m minus 1, where m itself is a prime. If n is not a prime, then 2 to the m minus 1 is not a prime. But if n is prime, then it may be a prime. Of course, not all such numbers are primes, as is the simple example tells us that for m equals 11, we get the number 2047, which is a composite number. But these numbers are very nice in the sense that there seem to exist infinitely many primes of this kind, although it's not proven. And since they have such a nice structure or such a nice representation, so in modern times it's very easy to test if such numbers are primes or not. And indeed, the largest known prime numbers as of today is a Mercenary prime. That's the number 2 to the 1, 3, 4, 6, 6, 9, 1, 7 minus 1. It's about 4 million digit long. Here is another formula, which was given by Euler. It's again very interesting formula. He looks at the formula numbers in the sequence m square plus m plus 41. And amazingly, the first 40 values of this sequence are all primes. The 41st value is not a prime, unfortunately, as can be easily seen, because 41 will divide everything. But the first 40 values are all primes. A similar formula is m square plus m plus 79, if I remember it correctly. Okay, you can take me to the task later on, but I think the first 78 numbers in that sequence are all prime. So it's very interesting. Why does this happen? I mean, m square plus m plus 41, such a seemingly innocuous looking formula, and first 40 numbers in this sequence are all primes. We don't know why, even today. Okay, so all this difficulty tells us that primes are not easy to capture as an entity. It's a although they are very easy to define, but not easy to understand. And if you recall, the question 2 asked, how many primes exist between 1 and n? Now, if primes are very chaotically distributed, there is no reason to believe, absolutely no reason to believe, that there should be some nice formula for this number, the number of primes between 1 and n. Absolutely no reason to believe that. So, in fact, that must have been a question which was asked by many mathematicians at the time, except for 2. Around 1808, Legendre and Gauss, perhaps independently, came up with a conjecture which is really amazing. Both conjecture that number of primes less than n converges to n over log n as n increases. It's very close. So that as n goes up, as the value of n increases, this number converges to n over log n. So it's an absolutely amazing formula that for such randomly distributed or chaotically distributed sequence as of primes, they seem to satisfy this wonderful formula. And on an aggregate level, we want to know exact total number of primes between a certain range, and there is such a nice formula for that. Well, that was conjecture, so we still didn't know at that time whether it's true or not. Gauss apparently used to calculate in spare times primes, larger and larger primes, and I don't remember exactly, but I think he computed primes up to 1 million or something, and he's fitted his formula in all the way up to that, and it seemed to work out beautifully. Log n, think of it roughly as a number of digits in n. Now, a student of Gauss, Riemann, well, he, to quite an extent, changed the face of mathematics by defining this zeta function. Now, zeta function has a very simple definition. Zeta of y is 1 plus 1 over 2 to the y plus 1 over 3 to the y plus 1 over 4 to the y extended to infinity. In other words, it's sum of 1 over m to the y, where m goes from 1 to infinity. And y is a complex variable here. Such a sequence was considered earlier also by Euler, but he only looked at y as a real number. So it was Riemann who was inspired to look at y as a complex number. For some reason, this turned out to be extremely deeply connected to prime numbers. It's not at all clear why such a sequence should have anything to say about prime numbers. It doesn't even have all the it has all the prime numbers, but it has many other numbers as well, all the composite numbers as well. And why is a complex number? It has neither prime nor composite. So why should it have anything to do with primes? Well, for some reason it does, and it has very deeply connected to many properties of prime numbers. In fact, as the zeta function and its properties were studied, mathematicians realized that understanding zeta function is key to understanding many properties of primes, especially the properties of distribution of primes. And this is a strong statement to make, but to an extent it is correct that the quest for understanding the zeta function contributed immensely to the development of complex analysis area of maths. Riemann not only defined zeta function, he also came up with a conjecture about zeta functions, and that again is an amazing conjecture. He conjectured that if you look at the complex plane and you consider the values of y where zeta function is 0, and if you, in some sense, you only look at there are some trivial zeros of zeta function. If you ignore them, then look at only the interesting region where for zeta function, then all the zeros in that interesting region of zeta function lie on a straight line. Now again, there is no reason to believe why this should have anything to do with prime numbers, but he noted some very interesting property, that is, if one can prove Riemann's hypothesis, then, for example, question 2 will be answered positively. That is, the Gauss and Legendre's conjecture that number of primes less than n are converging to n over log n, that will be true. Of course, till date, nobody has been able to answer Riemann hypothesis, so it's a major open problem in maths. But nevertheless, his definition of zeta function and formulation of this hypothesis led to a lot of interest, and many researchers studied the properties of zeta function. And building on the work of Zeeman and Chebyshev, finally in 1896, the question 2 was positively answered. Hadamard and Valley Poussin, I'm not sure about the pronunciation, Valley Poussin independently proved that the number of primes less than n converges to n over log n, which was conjectured by Gauss and Legendre. So we have answered question 2 as well, but it took a long time. It took about 2000 years to answer that. So okay, now it's not that these 4 questions were formulated 2000 years ago. These questions were perhaps formulated much later. But 2000 years of mathematical development finally resulted in the answering of this. Okay. Now let's go back to the formulas for primes, because the question 4 is what is left. Sorry, question 4 is already answered. Question 3 is what is left unanswered in my list of questions. So formulas for primes, as I noted, can provide a possible solution for this question. So it's not although the primes are, like I said, seem to be very chaotically distributed over the number line, but there were many formulae which were given for primes. The drawback in these formulae was that they did not tell us anything new. Let's just take one example. So here is a formula given by Willems in 1964. That P of n, that's a formula for prime n, equals, sine square of pi into n minus 1 factorial whole square divided by n, whole divided by sine square of pi over n. Now it's easy to show that P of n is 1 if n is prime, it's 0 otherwise. So it's a perfect formula for primes. Unfortunately, it doesn't tell us anything. It's simply based on the following property of primes, that n is prime if and only if n minus 1 factorial plus 1 is divisible by n. I just use this and you can realize that this formula will be the correct one. And like I said, in question 3 we have modified our question suitably to look for a fast method or fast way of determining if number is prime. And this certainly is not one such, because here we need to compute n minus 1 factorial, which really means multiplying 1, 2, 3, 4 all the way up to n minus 1. So far I've been saying fast method, but I have not really said what is a fast method. So this has remained a nebulous concept until 1930s, when this notion of computations was formalized by, amongst others, Turing and Church. And from then onwards, the development in the theory of computation led to precise definitions of the notion of efficiency. And now it becomes a fairly universally accepted notion of efficiency. And in terms of In the context of prime numbers, this is what we are looking for when we say a fast method of determining if n is prime. Count the number of operations performed by the method. So here we have a method, we just count how many operations does it need to perform. By operations, I mean basic operations, multiplication, addition, and such similar things. And we say that a method is fast or efficient if it takes at most a polynomial in log of n number of steps. Log of n, recall, is approximately the number of digits in n. So to put it differently, it's a fast method should take at most log n to the c steps for some constant c. Now with this definition of a fast method, let's look back to the two methods we know for determining if n is prime. One was the sieve of Eratosthenes. That required writing down all the numbers from 1 to n and crossing out all the non-primes. And that clearly requires one to check all the numbers between 1 and n, either cross them out or leave them uncrossed. So that will certainly require at least n operations, probably certainly more than n operations. And that, by our definition, cannot be an efficient method. Similarly, the Whelan's formula, as already noted, requires a computation of n minus 1 factorial, and that requires at least n minus 2 multiplications. So that also is not an efficient method. Question 3 was nearly solved in 72. Nearly because in 72, Gary Miller gave the first efficient method for determining if a number is prime. It takes roughly log n to the 4 many steps, many operations. So by the definition of fast method, it does satisfy this definition. The slight problem with this is that to prove the correctness of his method, Miller required to assume a form of Riemann hypothesis. And even though we believe Riemann hypothesis to be true, we still do not know if it is true. And perhaps proving Riemann hypothesis is much harder than proving that Miller's method is correct. So it is somewhat unsatisfactory, although since we all believe Riemann hypothesis to be true, his method is essentially solving question 3. But that was just the beginning of the work in this particular direction, because now, like I said, since the works of Turing and Church, the notion of efficiency, they did not fix the notion of efficiency, it was done later, about 1960s. But once the notion of efficiency was fixed, then one could have very clearly defined goals of what one is looking for. And soon enough, within the next few years, 2 more efficient methods came about. One was given by Solovay and Strassen. Theirs was an efficient method which was unconditionally correct. It did not require one to assume any hypothesis. The slight glitch was that their method could make mistakes sometimes. And what do I mean by that? Well, precisely when the number is composite, then the method had a small chance of saying it is prime. So the method actually required, or not required, the way their method worked was that it tossed some random coins. And based on the outcome of those random coins, it did certain computation. Now, if the outcome since it is tossing random coins, so there is a certain probability associated with the output of the method. And that is what I mean when I say that the method has a small chance of deciding incorrectly, that there was a small probability that the method will go wrong. But only when n is composite. If n is prime, it is always correct. Similarly, Michael Rabin, at the same time, modified Miller's algorithm, he removed the dependence on Riemann hypothesis from Miller's algorithm, but again he had to pay the same price. That is, introduce this tiny bit of error when n is composite. But for the practical purpose, this was sufficient, and indeed, the practical aspect of this particular question became important very soon. Around 1976, the notion of public key crypto systems was proposed. Now, these crypto systems are used to code information while transmitting. So, you have a certain sensitive information which you don't want anyone except the intended recipient to know about. So, what one does is you take this information, you code it using certain method, and then you send the coded message on the whatever communication medium you have, and only the intended recipient knows how to decode that. So nobody who's listening to the communication in between can figure out what is being transmitted. So that's what crypto systems are. Now Diffie and Hellman in 1976 proposed a notion of a very specific kind of crypto system, which they call public key crypto systems. These crypto systems allowed even two strangers to exchange secret information. And this is quite an amazing thing, because here is a sender and here is a receiver. Suppose they have never met. Now sender uses some method to code his information, sends it to the receiver. Receiver doesn't quite know how has the sender coded, but yet he can decode it. And even more amazingly, a third person who is listening to the communication cannot decode it. So it's a very, very amazing concept. And Diffie-Hellman proposed it, and they showed that it is actually possible to an extent. And within a year, Rivest, Shamir, and Edelman had designed a method which is a public key crypto system which works beautifully. And that's a well-known RSA system, and these days lots of financial transactions are actually based on the RSA system. So what have this public key crypto system got to do with primes? This is what. To make RSA work properly, we need large primes. These days, 160-digit large primes are very routinely used in RSA crypto systems. And to know such a large prime, the best way, or the only way essentially, is to randomly pick a number which is about 160-digit long and test if it is prime. Now, for a 160-digit number, which is of the order of 10 raised to 160, to test if it is prime, we need to know a really fast method, otherwise it will take forever. If he runs the sieve of Eratosthenes, for example, over here, then it will take forever. It will never halt. So, efficient method became important practically by the introduction of public key crypto systems. And that increased the interest. And fortunately, actually, by the time RSA came about, we already knew efficient methods for testing primality. The Rabin algorithm or the Soloway-Strassen algorithm, they were already present at the time this was proposed. So there was no problem. This method could be made operational immediately. In fact, the most commonly method used these days to test primality of large number is a variation of Rabin's method. But like I said, there was this tiny bit of chance of these methods going wrong. So researchers continued working on this to remove that tiny bit of error. And soon enough, in 83, yet another efficient method was proposed. Well, okay, almost efficient method was proposed by Edelman, Pomerance, and Rumeli. So their method is unconditionally correct and never makes a mistake. But it is not quite efficient, although it's very close. If you look at the number of operations it performs, it goes like log n to the some constant times log. Oh, I missed a log there. Read it as log n to the constant times log n. I've written it log n there, but it's really log n. So log n is a very small number. Somebody remarked that although log n theoretically goes to infinity, empirically it has been formed to be less than or equal to 4. But so all these methods, efficient methods, we have seen 4 efficient methods, they essentially give the answer of fairly satisfactory answer of question 4. It was only some theoreticians who were still not satisfied, although their numbers were not many, and they still wanted to know, okay, no, we really want to know an efficient and unconditionally correct method. So, to their satisfaction, a few months ago, we managed to find such a method. This method is efficient, it's unconditionally correct, and it never makes a mistake. So, question 3, therefore, is well and truly answered. So, I started with these 4 questions very conveniently because now we know the answer of all these 4 questions. And but there are many questions about primes which we don't know an answer of. So let me go through some of these. Here is the first one, and the most important one, the Riemann hypothesis. It's probably the most important unsolved problem in mathematics. Like I said, a positive answer to the Riemann hypothesis will greatly increase our knowledge about primes. And the icing on the cake is that there is $1 million prize, thanks to Mr. and Mrs. Clay on solving this problem. Another very important conjecture which remains unanswered is the Goldbach's conjecture, and this is a really long-standing conjecture. It was proposed in 1742. Goldbach was a contemporary of Euler. It's a very simple conjecture. It says that every number, or every even number rather, is a sum of 2 prime numbers. It has been verified up to, I don't know, 10 to the 20 or so, and it seems to be holding. So people believe this to be true, but we don't know really an answer of that yet. Another interesting conjecture is the twin prime conjecture. Now, twin primes are pairs of numbers, of prime numbers of the form n and n plus 2. Now, if n is prime, then n plus 1, except for one special case, cannot be a prime. So 2 and 3 are the only cases where both consecutive numbers are prime, because otherwise one of n and n plus 1 has to be even, so it can't be a prime number. N and n plus 2 can be primes, both be primes. And these are called twin primes. The conjecture says that there exist infinitely many twin primes. We don't know how to solve that. On the other end of the scale, so here twin prime conjecture is saying that often, or infinitely often, consecutive primes come as close as possible to each other. The other question here would be, how far can they go away from each other? We also have a conjecture for that. This conjecture says that if n is prime, then the next prime has to be less than n plus some constant times log n cube. The best we know as of now is that if n is prime, then the next prime has to be less than 2 twice n. Well, this has perhaps been slightly better, but not much. So there is a huge gap to cover there. We need to, the conjecture is, and it's perhaps believed to be true, is that the next prime is not too far away from it. Another very interesting question. We know how to test if n is prime efficiently, but we do not know how to factor composite numbers efficiently. That is, given a composite number, compute all its prime factors. We don't know how to do that efficiently. In fact, this security of RSA system is based precisely on this, on the assumption that we do not know, or not the assumption, that's the fact that we do not know how to factor numbers efficiently. And the day we manage to factor numbers efficiently, RSA system will be history. So many people actually will hope that no efficient method for factoring numbers can be found. Finally, this interesting notion of Coulomb's spiral, which was noted in around 60s, that if you draw the numbers in a spiral fashion, then prime seems to be concentrated along the diagonals. Well, you can put it more formally, that if you consider quadratic equations of the form am square plus bm plus c, and look at this sequence of numbers, then some quadratic equations have a high density of primes in their sequence, and some others have very small density of primes. So primes seem to behave differently for quadratic sequences. We don't know why. In fact, there is a very interesting story about discovery of this spiral, that during a particularly boring lecture, Coulomb was twiddling around in his notebook where he decided to draw these spirals and then noted this. So many times discoveries, or interesting discoveries or observations are made during boring lectures. And so I hope that many of you who have been twiddling around their notebooks for the last 1 hour, at least some of you managed to make some interesting discoveries. Thank you.